In this slidecast, we'll cover recursive search. Searching a vector can be accomplished using recursion, and the simplest way to search is a linear search. We examine one element at a time, starting with the first element or the last element, to see whether it matches the target. So on average, about n over 2 elements are examined to find the target in linear search, if you're assuming a random collection of values and random searches. Now, if the target is not in the vector, then all n elements are searched. So a linear search is order n. And the base case for the recursive search is an empty vector. The target can't be found, and the result is -1. And the first element of the vector matches the target. The result is the subscript of the first element. So those are two base cases. And then the recursive step is to search the rest of the vector, excluding the first element. So this should remind you, similar to searching a string. Now, if the vector is empty, the result is -1. If the first element matches the target, then the result is the subscript of the first element. Else we search the vector excluding the first element and return the result. This is the recursive case. Here's a C++ function. It's a template function where we can take a vector, we take a target value that we're searching for, and we take a position, pos first, which is the first position of the vector that we're searching from. So if pos first is equal to the size of the vector, we return a -1. It's not found. If the target is found at that position that's passed as our parameter, then we return pos first, that index number. Else otherwise, here's the recursive call. We call it with the same vector items, the same target value, and we have pos first +1. So we'll exclude the first item in the vector for the recursive call. Now we need a non-recursive wrapper function. So it's a wrapper for the recursive linear search function. This takes just a vector and some items. And what we do is we'll call linear search the 3-parameter case where we'll have items, target, and the 0, meaning this is where we're going to start our search. So this wrapper function gives us sort of a high-level abstraction that a user could call to search for a target in a vector, and then we'll use this private function that we've defined to do the search, where we'll keep track of this third parameter. Will keep track of where we are at in our search in the vector. So here's a trace. If we call linear search on greetings is an array, and we're looking for hello. If this is our array, our target is hello, we'll go ahead and call our linear search with 3 parameters, where we'll start at location 0. If we make that recursive call, we have greetings looking for hello at position 0. We will compare, we won't have the base case. The first item in the vector is hi, it doesn't match hello, so now we'll make a recursive call and we'll add we'll have position +1, which will mean now we'll call this function. We're looking at position 1. At position 1 we find hello, so hello equals hello. We'll return 1 as the index of where the result is, and that will just be returned as we unwind the recursive calls, and the result is 1, meaning we found the target at index 1 in our vector. Now, a binary search algorithm can be performed only if we have a vector that has been sorted. And our base cases are the vector is empty, or the element being examined matches the target. Now, rather than looking at the first element, a binary search compares the middle element for a match with the target. And if the middle element doesn't match, the binary search will exclude half of the vector within which the target cannot lie. So a binary search algorithm is going to be much more efficient than our linear search, and it's a powerful tool that we will see used throughout the rest of this semester. Here's some pseudocode for the binary search algorithm. We have our base cases where the vector is empty or the middle element matches the target. So we return the subscript of the middle element in that case. Otherwise, we will either conditionally search the vector before the middle element if the target is less than the middle element, or we'll recursively search the vector after the middle element and return that result if the target is greater than the middle element. So we have a choice here. We'll make one of these recursive calls, and we'll effectively be eliminating half of the vector space when we do that. So here's an example of searching for the target Dustin, and here's a vector of names. So first, middle, and last are the indexed to the first, middle, and last elements. And we'll start our search by looking at the middle, comparing Dustin to Elliot. Since Dustin is less than Elliot, we'll make a recursive search on the items before Elliot. So now we'll be searching into this vector. Now first, middle, and last are 0, 1, and 2 respectively. We'll compare Dustin to Debbie. It doesn't match, and Dustin is greater than Debbie if we do a string comparison. So now we'll search in the upper half of the vector. And in this call, our first and middle and last will all be equal to 2. We only have one element left in the vector, and as we compare that, it matches. At each recursive call, we eliminate half of the vector elements, making binary search an order log n search. This is the first log n algorithm we've seen this semester. So a vector of size 16 would search vectors of length 16, 8, 4, 2, and 1. So it would make 5 probes as the worst case. And a doubled vector size would require only 6 probes. And a vector with 32,768 elements would only require 16 probes, because log to the base 2 of that number is equal to 15. So a vector of 65,000 plus elements would increase the number of probes to 17. Here's a C++ implementation of our binary search, where we take a vector, an integer for the first and last index numbers, and a target value that we're searching for. If first is greater than last and we have an empty vector, we return a -1. If our target matches the middle, then we'll return middle. There's our base case for a successful search. Otherwise, we'll make a recursive call depending on how target compares to the middle item. And notice how we use first and middle to sort of reset these parameters to either search in the lower half of the vector if target is less than middles, or we'll search the upper half of the vector if target is greater than the middle value. And here's our wrapper function for this recursive binary search function. So here's our binary search that takes 2 parameters, our vector and the target value. And we'll call binary search with the vector, and we'll set our first and last to be 0 and items.size -1. So we'll start out by searching the full vector, depending on what its size. Here is a trace where we first call a binary search of a vector kids names for Dustin, and that will go ahead, and this is our wrapper function, which goes ahead and recalls binary search with 4 parameters. We set sort of first and last, in this case being 0 and 6. It doesn't match the middle element, so we'll search the lower half. Still searching for Dustin. When we miss there, the middle element is less than the target, so now here's where we finally just search position 2 and we go ahead and find a match. And then our 2 is returned as we unwind the recursive calls. So here's just a trace of the problem we saw earlier. Go ahead and stop the slidecast and study this carefully so that you understand all of the recursive calls and how each one was processed. Now, to test a binary search, You could test a vector that has an even number of elements and an odd number of elements, and then duplicate elements. And these two cases would be good to test so that we know that there's no math errors in terms of our dividing and trying to find the middle element when there's an odd number or an even number. We should test each vector for the following cases. The target element is the element at each position of the vector, starting with the first position and ending with the last. The target is less than the smallest vector element. The target's greater than the largest vector. And the target is a value between each pair of items in the vector. And that brings us to the end of this slidecast.